Okay. So, most of you know, I think that LHC is not only taking a huge amount of data, but is planning an upgrade that it's supposed to increase the amount of luminosity integrated by more than 1 order of magnitude. And we thought it would have been useful to start to introduce this upgrade. First, with the colloquium to the department to show the status, the perspectives, the needs in physics and the plans. And then more seminars, a little bit more specialized, but still of general interest. At the moment, we have planned 3 more, one on the potential of physics, and then on some technical on detector and techniques which are quite interesting, one on the timing layer and one on high rate readout for the CMS experiment. There will be more in the future, very likely. But today we will have an introductory colloquium on the status and perspective, so LHC endeavor and achievement. The colloquium will be given by Professor Gunther Dissertori. He is professor at ATH in Zurich, head of institute there, and presently deputy spokesperson of the CMS experiment. So the best person best suited to give this seminar, and I just give him the stage. Okay. Thanks for coming.
Grazie. Thanks a lot for the invitation. It's a pleasure to be in Padova, especially since the first time, actually, that I'm in Padova, although I was not born so far away, so it's high time that I'm here. So basically, Roberto already introduced the goal of this talk. This is supposed to be a general overview of what we're doing in general at the LHC, what has been achieved so far, and then a specific focus on the future. And I will introduce some of the challenges that we will have to face in the next 10 years or so. And as you have heard, then in the coming weeks and months, there will be dedicated talks on giving some more details. So here is the outline of the talk. Basically, it's just what I described so far. First, there will be a rather general description of what we're doing. Probably for the experts among you, it might be a bit, maybe a bit boring, because I suppose you know, well, you have to know all of this actually, but still I will try to give a didactic overview of what is happening, and then again, describe a bit the challenges. There's an important thing I want to mention right at the beginning. I will really focus on the CMS experiment only, mostly for practical reasons. I mean, not to be too long in the talk, and also because obviously I know that experiment best. But the general challenges that I'm going to describe apply to all the LHC experiments. It's not so much specific for CMS. So obviously one cannot start such a type of talk without mentioning the standard model of particle physics. I'm not going to describe now the standard model of particle physics, but this is the theoretical model that in the end we are probing at the LHC. We are trying to test, and actually we are trying to refute, or at least trying to find some cracks in this model. And again, I'm not going to tell you now what the details of this model are. I'm sure that most of you actually know pretty well. I just wanted to highlight one thing, which is actually for me probably the most amazing thing of this model, and it's the following. Once you have decided what the matter fields are that you want to describe, and once you have decided to assign certain charges to these matter fields and to impose a symmetry constraint, gauge symmetry, then basically everything is set. Then you cannot write down much. You can basically write down 4 lines of a Lagrangian. That's it. And that, I think, is the beauty of this model. It is so constrained, and still it then describes so many things. And the 4 lines are basically, the first line is just the dynamics of kind of radiation, or the dynamics of gauge fields. The second line is the interaction of matter fields with these gauge fields. The third line is the interaction of matter fields with the Higgs field, or those terms which give mass to the matter fields. And actually, this is one of the lines that we understand less in the standard model. There are many, many parameters which you have to put in by hand, actually. And the last line is the dynamics of the Higgs field. We know that the electroweak symmetry is broken, meaning we know that the masses of the W and the Z bosons are different from the mass of the photon. And the simplest description for this is this Higgs field, and this is basically the dynamics. So these 4 lines basically is it. And later on, I will come back to this Lagrange and say a bit more about this last line, which is going to be probed much, much more in the future. Now, overall, this model is very successful. In some parts, it has been tested up to better than % level, but there are a number of open questions, and I will come back to these open questions later on. So the game is not over here. Now, if you are trying to look for cracks in such a model, you can ask yourself, how do I explore the unknown? And basically, one can do it in 2 directions, or in a linear combination of these 2 directions. Either you want to try higher and higher energy or mass scales, or you study physics which has weaker and weaker coupling, so the effects are smaller and smaller, or probabilities to find something are smaller and smaller. Or you go in a direction where you require better and better uncertainty. And if you have more statistics, or if you have an experimental setup which gives you more and more statistics at a certain mass scale, basically you move in this direction. If you have an experimental setup that gives you more energy, like a new accelerator, or accelerator is more center of mass energy, you move in this direction. And the LHC was actually a big step in both directions in this last 8 years or so. Compared to the past, we made a step of a factor of 7 compared to the previous accelerators in this direction, and we got a lot of data. Now, the high luminosity LHC, this is what I'm going to talk about later on in detail, is going to be a huge step in this direction, because it, as Roberto already said, it will give us an order of 10 times more data. So we will move basically a factor of 10 in this direction. It will be basically running at the same center of mass energy. So you wonder why actually it's not going up straight. The point is, this is maybe more for the experts, since at the LHC we have protons colliding, and so you have to pick up quarks or gluons from the proton with a certain momentum fraction. The more statistics you have, the more likely it gets that you sometimes pick up a quark or a gluon that carries basically all of the momentum of the proton. But the probability to find such a situation gets smaller and smaller. So you need a lot of statistics to pick this out. But if you find such collisions, I will show this in the next slide, then you get basically, it's corresponding to have a bit more of energy. So that's why the HL-LHC does not go up straight. And of course, we don't know yet what is going to be the future machine, if there's ever going to be a future machine, but obviously the goal has to be that with such a future machine, we have to go in such a direction. But the talk today will be about this direction here. So how do actually collisions at the LHC look like? We collide protons. Most of the time, there are also other types of collision, but I will focus on protons here. And by now, we have already covered many center of mass energies, starting at 900 GeV up to 13 TeV currently. And the plan is, in a few years from now, to make the last step to the design energy of 14 TeV. And the design rate is that we have collisions every 25 nanoseconds between these bunches of protons. In each bunch, we have about 10 to the 11 protons. So this means we get 40 million bunch crossings per second. We get a lot of data. We'll come back to that in much more detail later on. And we can write out collisions to tape at the rate of about 1,000 per second. So there we have to do something. So we get these kind of collisions, and I will describe some of the challenges related to these collisions. And in the end, what we have to do is, of course, to compare what we measure in the detector with some theoretical prediction. So I use this picture now to describe a bit more what we are actually looking at the LHC. So this is, I think, the only equation I'm going to show. The basic picture is always the following. You have 2 protons colliding, and you pick up one parton, so either a quark or a gluon from the first proton, and the quark or a gluon from the second proton. These carry some momentum fraction, of the initial protons, and the real interaction, the interesting interaction occurs between these two partons. So since they carry a fraction of the momentum, also the real interaction we are looking at occurs at the lower center of mass energy than what you put into the accelerator. And then you produce some final state. And the general description for, let's say, the probability of producing some final state made of, for example, two particles D and C, when you start with two protons, so this is the cross-section, is just the probability for this interaction multiplying times the probability to find this parton in this proton and this parton in this proton. So in principle, it looks complicated, but it's very simple. The thing I want to highlight, and this is going to be relevant for later on, is the following. What we are typically looking at, or what we are interested in, is those reactions where in this moment here, there's a lot of energy and momentum exchanged, okay? And what do I mean by a lot? By a lot, I mean where the momentum which is involved, or the exchange which is involved, is much bigger than the proton mass. Proton mass is 1 GeV. So if there is a momentum exchange which is much larger than 1 GeV, say 100 GeV, then it gets interesting, typically for high energy physics, okay? The problem is the following. If you look, what is the total probability that just anything happens? I give you two protons, you collide them, and then you see what is the probability or what is the cross-section that anything happens. That is a certain number. It's 100 or about 100 millibarn. But the probability that something happens with a lot of momentum transfer is much smaller. For example, the probability that the W boson is created here, and the W boson has a mass of 80 GeV, so this is a hard scattering. There is a lot of momentum exchange. The probability for that is about 1,000,000 times smaller than that just anything happens, okay? Meaning, if I want to produce a W boson, and I give you protons, I have to give you at least a few million protons that you have to collide before you will see the first W boson. So you see that most of the collisions that we produce at the LHC are not really of interest to us. And so we have to do something about this, okay? So another way to look this, well, there's one other aspect I should mention. We know that the number of events of a certain kind that we observe in a detector is given by this cross-sectional group, the probability to produce this event, times the so-called luminosity. The luminosity is kind of a flux factor. It's basically related to the flux of these incoming protons, okay? So if you want to measure a certain process with a certain statistical uncertainty, you need a certain number of events before you can say something statistically significant. And to get a good number of events, you need either a large enough cross-section here or a large enough luminosity, or both. So if you are looking for something which is very rare, which has a very small cross-section, it's clear that you need a lot of luminosity before you get enough events, okay? And another way to look at it is the following. This looks like a complicated graph, but it's not so complicated. Let me guide you through it. What we have here is the center of mass energy of proton-proton collisions. Let's just focus on one region here. And this is the cross-section for different type of processes. And as I said before, the total cross-section is about 100 millibarn. So this just, again, the probability that just anything happens. And in fact, what typically happens is that the protons, when you collide them, just break up, okay, and give some particles. So in fact, the most likely thing to happen is that the protons collide. There might be some momentum exchange between quarks and gluons. They just scatter, but the momentum exchange is just of the order of a GeV or so. And in these cases, the protons break up. You produce a certain number of particles, and these particles have not a lot of momentum. Again, a few hundred MeV, and not 100 GeV or so. And in fact, the very first event that we ever saw was such a kind of event, where we just got a few charged particles, say a tenth or so of pions and a few neutral pions, and those particles had a few hundred MeV each. Of course, the very first event that we ever saw in 2009 could have been a Higgs boson, but what we saw was the most likely thing. it was not excluded that it could have been Higgs boson. So this is the most likely thing you're going to see. Then, if you run your collider a little bit longer, at some stage, you will have enough collisions that you will see something which is a little bit less probable. The next thing, which is a little bit less probable, is that you still have scattering of quarks and gluons, but now they exchange more momentum, or let's imagine they come closer to each other. And then the outgoing quarks and gluons carry much more momentum than just 1 GeV, and they end up as so-called jets of particles in the detector, okay? And depending what the momentum of these jets is, it is the smaller the probability to find such an event. This is kind of just the Rutherford scattering. And then you take a few more million collisions. I just continue to give you protons. And after a few more million collisions, you might see the first Z boson being produced, where a quark and an antiquark annihilate. A Z boson is produced, and then, for example, the Z boson decays to a muon and an antimuon, or to an electron and an anti-electron, and you see this very clear signature in the detector. One thing to highlight here is the following. Of course, once you produce a Z boson actually decays to quarks more often than to leptons. But those cases you don't see. Why? Because this Z decay to quarks would very much look like this here, but these kind of events are order of 1 million times more likely. So it's just buried in a huge noise and a huge background. That's why we look for Z bosons or W bosons via the leptonic decays, because then we clearly see them. I mean, there's much less background. Then you wait another 1,000 more, a factor of 1,000 more collisions, and you will see the first top quarks being produced. Top quarks are very heavy, so the likelihood to produce them is smaller, the probability to produce them is smaller, so you have to wait longer. And if you wait even longer, you start to produce Higgs bosons. So in this way, since we got a lot of collisions already by now, basically in a rather short time, over a few years only, we scanned this whole graph here. So basically we've tested these different type of processes which have probabilities that vary over 9, 10 or more orders of magnitude. So already this is pretty amazing. If one thinks about how many orders of magnitude these are, it's quite impressive. We just take it always for granted, but sometimes it's good to think about it. And in fact, we got a lot of collisions. This is a graph which shows as a function of time during the year the number of collisions we got. We call this integrated luminosity. It's a measure of how many collisions actually the accelerator provided to us. And it starts in 2010, and in fact, there the curve we have to multiply by 50 in order to see it on this graph. And this is the latest curve, and you see in 2017, we got a record luminosity for all these years so far. And if you compare the number, in 2010, we got 45 inverse picobarn. This is a certain unit. And we were extremely excited and happy about this amount of data in 2010, I remember well. This year, we got a factor of 1,000 more. So in 7 years, the accelerator basically improved by a factor of 1,000 in amount of data delivered. Also, this, I think, is a big number. When you have a machine, typically, you do not easily improve a machine by a factor of 1,000, whatever machine it is. And of course, having such a huge amount of data, now we got access to cross-sections, so processes that are very, very rare. And this is often displayed by this diagram. It also looks very complicated, but let me guide through it, and I'm not going to explain all the details here. What is shown here is just a list of all different types of processes that can occur that we study, as I showed you before. For example, processes that involve WZ bosons, all kinds of processes that involve 1, 2, or 3 WZ bosons or photons, processes that involve top quarks, or processes that involve the Higgs boson. And what you see are data points in different colors. These are just measurements at different center of mass energies, and you see gray lines. Sometimes you don't see them because the data point lies on top of it, and these are the theoretical predictions. And the message of this plot is the following. There are basically two. The first one is we have, in the 7 years, already measured many, many, many processes that, again, cover a range in probability or in cross-section that is about 9 orders of magnitude or so. The second message is that data basically always agree with the standard model, so no crack found so far. And this, of course, is a huge success for the theory, but of course, it's also a bit disappointing for the experimentalists who try to find deviations here. Often this plot is called the stairway to heaven. I mean, it looks like the stairway, right? But actually, I tend to call it the stairway to hell because, well, first it looks like it's going down, but that's not the reason. Because we are now hitting, in many cases, what I call a systematics wall, and I will describe it later on what I mean. We are, even now with a lot of statistics, the problem is, in many cases, is not the statistics anymore, but really the systematic understanding of our measurements. And then it gets very challenging, but probably more interesting also for the students, because then you really have to start to use your brain. So if we want to summarize basically on a single slide where we are now, this is a very condensed summary of where we are now. Regarding the Higgs boson, where we have found it, and we know, or if we have measured the coupling of the Higgs boson to vector bosons, so to the W, the Z boson, with a precision of about 20%, 15 to 20%. And we see that it couples as we expect, as the standard model predicts. We also have observed that the Higgs boson couples to tau leptons, as predicted. And we also have first evidence that Higgs boson couples to B quarks and to top quarks. Again, as predicted by the standard model. In fact, the standard model basically tells you, the Higgs boson mechanism tells you that the heavier the particle, the more the Higgs boson couples to it. And this is shown on this plot, particle mass versus kind of coupling strength. And you see there's this nice behavior. Again, the data points lie on top of the theory prediction. What we notice here is that so far we have measured the coupling of the Higgs bosons to the heaviest fermions. These, the tau lepton, the B, and the top quarks are the heavier fermions. And this is because they are heavy, they couple more often to the Higgs boson, therefore the Higgs boson decays to these particles more often than to other particles. And that's why so far with the statistics we have, we could see this. But of course we would also like to see if the Higgs boson couples to lighter particles as predicted. I will come back to that later on. So in a nutshell, we have tested so far the Higgs mechanism at the 15 to 20% level. It's already not bad, but we would like to do better, much better. Then there have been many searches for new physics, like supersymmetric particles, maybe new forces that are transmitted via new types of heavy Z bosons or W bosons, and none has been found so far. So basically, again, in a simplified manner, we can say that SUSY particles, they must be heavier, like sporks or gluinos, they must be heavier of about 2 TeV or so, otherwise we should have seen effects. Or heavy partners of the Z and W bosons, they should be heavier than 3 to 4 TeV, 3 or 4,000 GeV, otherwise we should have seen effects so far, okay? And since we have not seen anything, there are many limits, basically saying this and this and this model is excluded up to a certain mass. Then some very rare processes have been observed so far, like the BS meson. This is a meson made out of B quark and a strange quark that decays to 2 muons. This is a process that is very unlikely to happen. It happens only in 1 billionth of a time. But since we have so many data, we saw this decay. And this was an interesting decay because many theorists predicted a deviation from the standard model to be seen. We don't see it. So far, the measurement agrees with the standard model, but it's not very precise yet. And the studies of such mesons, of these kind of mesons that contain a B quark or, for example, a strange quark and their behavior, there are some deviations actually from the standard model seen, especially by one of the experiments. And these deviations actually look like as if there would be a so-called lepton flavor violation, meaning that it seems they behave differently if they decay to electrons or muons or taus leptons, while the standard model says it should always be the same. Now, these deviations are not yet super significant statistically, but maybe they are the first hint that something is not working after all. So this gives then an incomplete list of open questions, namely, with the current precision or with the current systematic understanding, we have started to probe the Higgs boson, but we would like to do much more precise tests of the Higgs boson. And as I said before, we have seen the Higgs boson decaying to heavy particles, but we would like to see it decaying to lighter particles like muons or charm, quarks, and so on. But since this is very unlikely to happen, we need much more data. So order of, for now, 10 times or more data than we have so far. Another obvious question is what gives mass to the Higgs boson? The standard model says it's the Higgs boson itself, because the Higgs boson couples to itself. But we have not yet experimentally tested this. So this is a very important test to be done. Many models say there could be more than one Higgs boson. So far, we have seen only one. So it's, again, important to check it. And another question which is there since long is, why is the Higgs boson actually so light? It's relatively light. It has a mass of 125 proton masses. The Higgs boson actually feels very much quantum fluctuations in the vacuum. And because of this quantum fluctuation, actually its mass should explode, should be much higher. So the question is, what is there some other physics effect which we don't know and so far that protects the Higgs boson from exploding? And maybe these anomalies that I've described before, maybe they are the new glimpse of such new physics. And as I said before, the problem is that in many analyses already, we are hitting the so-called, well, I call it the systematics wall, meaning that if you look at certain measurements, for example, the Higgs boson measurements, this is a measurement which tells you what is the rate of Higgs bosons produced relative to the standard model prediction. So if it's 1, it means it agrees with the standard model prediction. But what is relevant here are the uncertainties. There are statistical errors and there are systematic errors. And if you look at these numbers, you see that the systematic errors are equal or larger already than the statistical ones. Meaning, if you just get more data, your precision will not improve unless you understand better the systematic uncertainties. This is another case where we see the Higgs boson decaying to 2p quarks. And we only see it now at the 3 sigma level, so we are in the very early stages, and already now we are basically dominated by systematic uncertainties. These are related to theory uncertainties, or to, for example, how well we measure certain types of quarks, for example, the B quark. So this means we have to think a little bit harder. We have to think, how can you go around maybe the wall or break the wall? And there are several ways to do this. The obvious way is just look for something which is very, very rare, because then by definition, you basically just need statistics, okay? So look for very rare things. Or you go to other regions of phase space which you have not yet measured, and again, almost by definition, you will be then probably more statistics limited and not so much, maybe have not so much to worry about systematic uncertainties. Another way to look at it is, if we get more data, then we can do more precise calibrations, more studies of how the detector works, how we simulate detector, and then in the end, this helps to reduce the systematic uncertainties. Another way is to ask our theoretical colleagues to do better in their calculations. I mean, there has been enormous progress already, but still further progress is needed. And another thing to look at it is sometimes it's a question of what is the right observable? What should I actually measure? Because sometimes there are other kind of observables where I don't need so much precision in order to get sensitivity to some deviation. So it's really sometimes a question of what is the best thing to measure? Maybe it's not just the inclusive rate of Higgs boson, but something else, which gives me more access to new physics. And of course, and this is written in red, first of all, you have to make sure that you have an experiment or detector that gives you the best possible data, because if that is not the case, you can forget about the rest. So that's why so much effort is going to be invested, or is already invested now, and the next 10 years or so, to make sure that also in the future we will have a detector which is as good or even better than what we have right now. In fact, this is the plan. We have started in around 2010. Now we are in 2017. At the end of next year, there will be a shutdown, starting a shutdown of about 2 years. Then we will run for another 3 years, which brings us to 2023. And then we will have a long shutdown of 2.5 years where the accelerator will be upgraded a lot. And the experiments will have to be upgraded a lot, because then afterwards the accelerator is supposed to run at a luminosity, kind of an intensity, which will be higher by a factor of 5 to 7 or 8 or so. And then we will get much more data, a factor of 10 times more data until the mid-30s compared to what we expect up to 2022. And in order then to be able to, in fact, to make use of all this data, in this long shutdown, we will upgrade also the detectors, and we upgrade them a lot. And this is what I will talk later on. Another way to look at this plan, because this is a linear kind of plot, it doesn't impress so much to look at these numbers. It's more impressive to look at in this way. So this is the luminosity expected. This is where we are now. This is where we will be in 2022, 23. And this is where we will be at the end of HL-LHC when I will retire in 2035. So actually this is up to scale, because what is shown here is a giraffe. This is 6 meters, this is 60 meters, and this is 600 meters. This is in Shanghai. So the relative scale is correct. And I think this gives a bit of a different impression what it actually means, what's going to come. So very briefly, what do you want to do with so many data? First of all, we want to test the Higgs boson couplings to all these other particles at the few percent level. As I told you before, now we have them at the 15 to 23%. We want to test them at a few percent, because if there are any deviations, they cannot be much bigger than a few percent, because otherwise we would have seen effects in other places. Okay? So it's very important to push this as much as possible. And one of the key observables will be to measure these Higgs self-interactions. I will show it on the next slide. Then the searches, of course, for new physics will continue. One will start to look in new regions of phase space, maybe some regions of phase space where we are not yet able to see anything, or where, for example, SUSY particles are only produced via weak interactions and not via strong interactions, which we have been looking so far, mostly so far. And these flavor processes, these B mesons will be studied in more detail, or the top quark will be studied in more detail, just to check that maybe if these deviations that we see now are real, then we should see them very clearly. And then this would be really the first crack, real serious crack in the standard model. Or they go away. But this is very important to test. Now, in fact, as I said, one of the most important processes to measure is the production of 2 Higgs bosons, not only one as we are doing right now, because if you produce 2 Higgs bosons, then you are sensitive to the coupling of 1 Higgs boson to 2 Higgs bosons. So basically you are sensitive to the coupling of the Higgs boson to itself. And then you test this last line here, especially the potential. And why is this so important? I mean, in the end, you test the potential of the vacuum of the universe. I mean, this is, I think, important enough. And the problem is this process here, basically the probability to measure 2 Higgs bosons is 1,000 times smaller than to produce 1 Higgs boson. That's why we need so many data. Otherwise, we will never see it. And in fact, even with all this data, in the end, we might be able to measure this process only at a level of 20, 30%, we will see. And then we will start to look for rare Higgs decays. As I said, for example, the Higgs decaying to muons, or the Higgs decaying to a Z boson and a photon, or the Higgs decaying to something that is not seen. For example, if dark matter has to do something with a particle, and if the Higgs somehow is coupling to the dark matter, we don't know, it could be that the Higgs boson decays to dark matter particle, then these decays would not be seen. So this kind of very rare process will be accessible with much more data in the future. Then also the searches for new physics will go on, and we'll be able to look for a much larger phase space, as I said before. We might then study much more detail, for example, supersymmetry or supersymmetric particles that are only produced via weak interactions, meaning in much rarer ways than what we're looking for now. Or we might look for things which experimentally are very difficult. For example, if the supersymmetric partner of the top quark exists, it's called the stop quark. And if the difference in the spectrum between the stop quark and the lightest supersymmetric particle is about the mass of the top quark, then you have a problem, because this particle decays to a top quark and this particle here. And if the mass difference is just the mass of a standard model particle, then in the decay, the standard model particle almost has no energy left. And then the particles produced in the detector are all very soft, and it's never good for us, because it's more difficult to measure them. So these are kind of things which are very difficult to measure. And just to say that there is still a lot of room actually to find new particles, look at these numbers. The reach with all this data in the future, for example, for a heavy Z boson or W boson goes up to 6 TeV or so. As I said before, now we have 3 to 4 TeV. So this is quite a huge range. So if people tell you basically the searchers at the LHC have found nothing and it's over, and this is not true. So what are the experimental challenges and some proposed solutions? First, a preamble. Of course, I have to describe some aspects of the CMS experiment. But the main aspects are the following. It's, as you know probably, it's made out of several subdetectors. There is an inner part which measures the trajectories of charged particles. There are calorimeters which measure the energies of particles. There's a huge magnet. And in the outside, there's a system which measures the path of muons. Another way to look at this is the following. We look at this from the side, so we see it again. So in the inner part, we have these many layers of silicon detectors with which we can measure very precisely the tracks of charged particles. Then we have an electromagnetic calorimeter with which we measure very precisely the energy of photons and electrons. And then we have a hadron calorimeter which we measure, for example, pions, neutrons, protons, and this huge magnetic solenoid. Because of this, the charged particle tracks are bent. And then outside, if any particle goes outside, is still visible outside here, it's a muon to a very high degree of likelihood. So we have to measure the track of these muons, and you do this with muon chambers. I don't say too much about muon chambers here in Padova because it would be embarrassing because the world experts on muon chambers are here, so rather don't say anything because I'm not such an expert. What I want to highlight is the following. So this is is our picture, what's going on. In a collision, we produce charged particles, we produce photons, neutral hadrons like neutrons, and muons. What we measure are tracks of charged particles, basically a set of points in our tracker. We measure energy deposits in the calorimeter. These are energy deposits, and sometimes we measure muon hits outside. So what we can do is the following. We can try to combine the information from all these detectors in order to optimally use all this information instead of just looking at the tracker or just looking at the calorimeters. For example, if you see charge tracks pointing to energy deposits in the calorimeter, you can basically take the information from the tracker typically, which is much more precise than the calorimeter, unless the particles have a lot of energy. And then you take out these clusters, and then you see if some clusters remain. And then these very likely are related to photons, which don't leave any track in the tracker. And so, step by step, you combine all this information. And this gives you actually the most precise measurement of the overall energy or momentum flow, or as we call it, the particle flow. And why is this very useful? The intrinsic reason is the following. Actually, in a generic event, about 60% of the whole energy goes into charged particles. And about 30% goes into photons. So if you measure precisely charged particles and if you measure precisely photons, then you have caught 90% of the energy flow very precisely. And then it's not so important if you measure neutrons not so precisely, for example. And that's why it's so important to have a very good tracking system and a very good electromagnetic calorimeter. That's the deep intrinsic reason. And that's why you put more money on these kind of things. And of course, you have to make sure they have a good muon system outside that you catch also these very precisely. But there are a few real challenges. The first one is called pileup. So again, let me remind you, these are what we expect as luminosities after this long shutdown 3. What does this number mean? Let's just make a simple multiplication exercise. If you want to calculate what is the number of simultaneous proton-proton collisions when two bunches cross, you just have to do the following calculation. You multiply this luminosity, this is kind of the flux coming from the machine, times the total cross-section, namely that anything happens, times the bunch separation time. So this is the luminosity times the total cross-section. Then we have a bunch coming in every 25 nanoseconds. If you do this calculation, you get a number of around 150. Meaning, in the future, we will have, for each bunch crossing, 150 proton-proton collisions at the same time. It's like having overlaid 150 images of something. What are these 150 events? They are going to be the most likely thing, of course. So meaning, basically it's an overlay of 150 soft proton-proton breakups, where on average you produce about 6 charged particles per unit angle, and we cover about 10 units in angle. So this gives about 10,000 particles per collision. You multiply this number times this, then you get about 10,000 particles per collision. So this is the challenge. And you should be able to measure all these particles. So obviously, you see immediately you need a very granular detector to reduce the probability that 2 particles end up in your same detector element. In fact, it looks like this. This is a picture of such a simultaneous, I think this is about 130 simultaneous proton-proton collisions. These are the reconstructed vertices where all these tracks come from. They are distributed over a distance of about 5 to 7 centimeters. Or in time, it means they are distributed over a time of about 200 picoseconds. Now, we register such a collision if, for example, 2 of these tracks, we identify them to be very energetic. For example, you find a muon and an anti-muon with energies of 50 or 100 GeV or so. And you reconstruct it, that they come from the same vertex. Then you say, for example, here could be a Z boson that was produced. And maybe the Z boson came from a Higgs decay. So this is where the trigger tells you, now let's register this event. What are all the other ones? As I said before, all the other ones are just the most likely thing to happen. So all the other ones are this soft breakup of photons. What actually is relevant here is not so much the total number of simultaneous collisions, but it's the density of where they happen. For example, this shows the density of these vertices. At the LHC, as we had in the past or now, we have about 0.3 per millimeter. Means we have a vertex about every 3 millimeter. And now if you can reconstruct from these charged tracks by extrapolating them, if you can reconstruct a vertex where they came from with a precision of about 1 millimeter, then you are in business, because then if they are separated by 3 millimeter on average, you can distinguish them. However, in the future, we will have densities above 1 or almost close to 2, meaning that the vertices will be separated by 0.5 millimeter. And now if you have a resolution of 1 millimeter, you start to merge vertices. Then you cannot distinguish them any longer. So then you have a problem, and you have to think how to solve this problem. In fact, already now, or in last year, and this year is even worse, we have these kind of collisions where in last year we have about 25 interactions at the same time, and this year we had up to 50 interactions at the same time. So we are already somehow used to this situation, but at the high luminosity LHC, the situation will be a factor of 3 or 4 times worse. So that's why we have to do something about it. And what helps us is, again, this particle flow concept, because for every vertex, you could imagine this is an event which produces charged tracks, which produces deposits in the calorimeters. So if you can reconstruct those very precisely, you just subtract all those calorimeter deposits, all those tracks which come from other vertices, and you clean up your picture, basically. But the cleanup only works nicely, again, if you are able to distinguish pretty well these vertices. Another challenge is what we call it trigger. And again, we have the real experts actually sitting here. The problem is the following. We have 40 million collisions per size of 1 to 2 megabytes or so. So this finite bandwidth where we can store is fixed. You have a lot coming in, and you cannot write out much. So what you need is a machine in between that basically does a filtering. So this is just a filter. And our filter has 2 levels. The first one is what we call the level 1 trigger, and the second one, what we call the high-level trigger filter. And these triggers have some knobs where you can turn. Why do you need knobs? First of all, if the rate with which a certain kind of events comes in changes, you have to adapt your filter because down here you have a fixed bandwidth. And these knobs allow you to select what you're actually going to filter. You can choose what you want to filter. You can choose just to write out the boring soft proton-proton collisions. You can do that. If you're not interested in that, you want to use your tape in another way, then you have to do something here, change something in the filter to write out, for example, only events where there was a muon with 50 GeV or so and more. Since we have to be fast in deciding what you want to filter out, at the moment we take information from the calorimeters and the muon systems because there are not so many channels, so it's easier to elaborate all this information, and they give us fast information. And at the moment, the numbers are that from the overall rate, we can reduce here the rate to 100,000 per event and going down to 1,000. And up here, we have time. We have 3.6 microseconds time to take a decision if we keep this event or if we don't keep the event. Now, in the future, since the rate up here will improve, will go up by factor 5 or 7.5, we have to do something about it because otherwise it would be kind of sad. We get more data in and we still write just this fixed bandwidth out. So the goal is to increase basically these rates also by a factor of 7.5. In order to do that, we need a bit more time on the electronics to take a decision, to do some calculations. So we increase this time, but in order to do that, you see immediately you have to exchange a lot of electronics which sits on the detector, because all this electronics which sits there has been kind of produced to just work with this time. So we have to change electronics to get more time. And another important thing is, in the future, we also want to take information from the tracker. That's a lot of information. Okay, so we have to do about something. In fact, the other challenge related to triggers is the following. What we like to see is, for example, muons that could come from a Z or W decay. And the Z and W could, for example, come from a Higgs boson. And such muons, they typically are what we call isolated. So there are muons where there are not too many particles around. Most of the muons that you will see in your detector are actually muons that come from decays of, for example, pions or kaons. And those muons would appear in this, for example, in this jet, so where there are a lot of particles around. So in order to very quickly find a muon that could come from a W or Z boson, you look for muons that are isolated, so where there are not many particles around. So you should be able to calculate quickly on the trigger level on your electronics if there's a lot of energy around or not. At the moment, we only can take the information from the calorimeters to do this. The problem is depicted here. So this shows the momentum of these muons and the rate of muons coming in. So if you don't do anything, you just take every muon that you see, you would have rates of, this I think is 10 to the 7, 10 millions per second. You cannot write them all out. And in fact, most of these muons, really most of these muons, are these muons coming from the decays of things that we are not so interested in. If you start to select muons that are very energetic, let's say above 30 GeV or 20 GeV or so, you start to select muons that could come from Z or W decays. These are the muons that you want to select. Now, the problem is, in the future, this whole rate, this whole curve will go up because the luminosity will go up. Then you have a problem. So what do? So you could either shift this threshold here to higher values, so then you reduce again. That's not so nice, because then you would also throw away many muons that are actually interesting. The other way is try to reduce this background in a more clever way. For example, calculating already in the tracker if there are other particles around or not. But then you need information from the tracker in the trigger, so immediately in these few microseconds. Today we don't have that. So all these challenges give us the detector requirement. So you need a very granular detector that is fast, and it is radiation hard. So some of the detector parts we have to replace simply because these detector parts have seen already so much radiation that they start to degrade. So this will help us to minimize this pileup. It will help us to reconstruct very efficiently the vertices and reduce the pileup. And as I will show, timing is a very relevant information. And to show this in a bigger thing, this is just in a snapshot of what we are going to do. So all these electronics for the trigger and all the detectors will be exchanged so that we have this larger bandwidth. The complete inner tracker will be replaced. The forward calorimeters will be replaced, and the electronics on the muon chambers will be replaced, and some beam radiation and luminosity measurements will be upgraded. And as I said, or as Roberto said in the beginning, you will hear much more details about all these upgrades in the future talks. What one should highlight here is that this upgrade is of a very large scope. This is not just replacing a little bit, a few boards here and there. This is of complexity and size, I think, which is not too dissimilar from the complexity of the original construction project. One really cannot, one should not underestimate the complexity of this upgrade. We are replacing important parts of the experiment. Now, Joel Butler, the spokesperson, uses to say CMS likes to do bold project. This is definitely a bold project. And in fact, there will be many contributions, important contributions from Italy. And as I know, Padova is thinking of contributing to several of these upgrades. Just in concluding a few examples, as I said, there will be a completely new silicon tracking system, which is much granular. Actually, this will be the most ambitious, I think, tracker construction ever made in a collider experiment. And we think that with this replacement, we will have as good or even better tracking up to the ultimate luminosity of TLHC. And one highlight of this is the following, that the tracker is designed such that we can measure basically the momentum of tracks very early on. And in fact, such a layer is actually made out of 2 layers of silicon detectors, which are very close by. But they are connected by some chips, which will look if there is a hit here and here, and if they are close together so that it could come from a particle which has, for example, at least 2 or 3 GeV. If they see 2 hits that are far away, these either come from a particle which is soft, so has not much energy, or they are not connected at all. And if you reconstruct very quickly these so-called stubs, and you have a few of them, then you can actually reconstruct very quickly the spending of charged particles. In fact, per event, we will have about 15,000 of such stubs that they will be put at 40 megahertz into a lot of very good FPGAs. And these FPGAs, basically, we will have 5 microsecond time to reconstruct all these tracks. So today, we cannot do this. And this will help us a lot, because this will give us tracking information which is very precise already very early on in this whole chain. Another example is that we will replace this whole forward calorimeter. I will not go into detail, but this will be a calorimeter made out of kind of layers of silicon and silicon detectors and tungsten and brass absorbers. This will be a calorimeter which is made out of, I think, 600 square meters of silicon and 6 million channels. This is the first ever at the collider experiment to have such a highly granular calorimeter. With such a granular calorimeter, we should be able to reconstruct really the details of a shower, particle shower in a calorimeter, which again should help then to reduce pileup and so on. So this is a super ambitious project. And finally, you will have a dedicated talk on this. Timing information is very useful. As I said before, these vertices, these whatever, 150 vertices, so they are distributed over 200 picoseconds. So instead of just showing this picture, you can show this event in 2 dimensions. This is the Z dimension as before, and this is the time dimension. So basically, you blow up these vertices and distribute them in time. So you see they are distributed over plus minus 200 picoseconds. And now the idea is the following. If you can slice this picture into many slices, and where the slices, let's say, are about 30 picoseconds thick, so if you also can measure the time of a certain particle, then you go from this whole picture to just 10 or 15 pictures where the number of vertices is much reduced to a number that we know to handle because we are handling them already now. This is the simple idea. So the proposal is to put in some layers of detectors that are able to measure the time of these particles with a resolution of 30 picoseconds. And then I don't go into detail of these diagrams, but basically it tells you that even if the density of these vertices will increase a lot, the probability that we do wrongly assign this density will stay low. Or I think another number which is much more interesting is the following. We have simulated that if we include such timing information, with the same amount of data, we would be able to collect 30% more of such events where there are two Higgs bosons. Now, this 30% doesn't maybe sound so much, but think or try to calculate how much it costs to run the LHC 30% for a 30% longer time in order to get the same statistics. And I can tell you it's many millions. Because running the LHC over a year is expensive. So investing now in such a detector actually has a huge effect. So concluding, basically quoting here Michelangelo Mangano, is there are three scenarios. The first scenario is no matter what the LHC finds, we will have to measure as precisely as possible all the properties of the standard model, much more precisely than we are able to do now, especially, as I explained before, the properties of the Higgs boson. This we will have to do in any case. Now, there's a scenario that the LHC makes a discovery. Then, obviously, we will have to study with this much more data what we actually have discovered, because the discovery with discovery as such, you won't know much. It could be a heavy vector boson, it could be related to a new interaction, it could be a particle that looks like a dark matter particle, but it's not clear in the beginning if it is dark matter, if it's something else. It could be something unexpected. So, of course, this is probably the luxury scenario. And finally, this is probably what we are in right now. We still don't know what's next scenario. We don't know yet what is the next machine. But one thing we know, the high luminosity LHC is the only machine today in the high energy physics that is guaranteed. This is a proof, this is going to come. So we have to make sure that we exploit this machine at the best possible way. So here are the conclusions. There is one thing which is different today than, for example, 10, 15 years ago. 10, 15 years ago, we knew that there was a mass scale where we should discover something, which was about 100 to 1,000 GeV, related to the electroweak symmetry breaking. There was a theory told us there is a mass scale where something has to happen, and something happened. The Higgs boson turned up. Today, we find ourselves in a position where the theorists cannot tell us where the next mass scale is. It could be 3 TeV. It could be the Planck scale. So this is a pretty different situation. So now I think we are really entering this region of complete exploring of the unknown territory. So we have now a gold mine in hand, after all. It's the Higgs boson. So we will have to study it in much more detail, and we have to try to look for cracks in the standard model wherever we can. And one thing is sure, precision physics has come. Typically, one thinks of a hadron collider as not just as a discovery machine, but the LHC is a precision machine by now. And what I really would like to highlight here, and especially for the young people, you should not think that there have already been so many publications, so everything has been done. There's no room for new ideas. Actually, there's huge room for new ideas. Because as I showed you, often we are systematics limited. So there's huge room for completely new ideas, either for new methods of how to analyze the data, of new ideas for observables. Now there's all this machine learning is coming up, it's an enormous hype, but I think it will change quite a lot how we do data analysis in the future compared to how we did it in the last 100 years or so. So really, your brains will be used very well in these future years. And I try to show that the detector upgrades that are being planned now, and we start to do them actually, they try to address all these challenges that I described. So thank you much for your attention.
Okay, so thanks a lot, Gunther, for the clear and very nice seminar. I imagine we have time for questions. Who wants to start?
I think it's more a comment for the students, because I think for the colleague is clear. The main purpose of this presentation is to stress the importance to increase the statistics with a high luminosity. It is important as well to increase the energy. Anyway, someone could have in mind the transparency of the systematic wall. So can have the impression that we already reached the limit of the systematic, so it's useless to increase the statistics to reduce the statistical error. But you have to keep in mind 2 points. First, this is not true for all the measurement. For most of the measurement, we still are at higher statistical error, so it will be important to reduce the error with higher statistics. And second point, there is a relation between the statistics and the systematic error that look like strange if you learn, but we use to estimate the background for several measurements with a method that is called a data-driven method. And so we select a region, a control region far away from the signal, and of course if you still have few events, this increases the systematics. So it's not true that we are at the limit. There is a lot of space to reduce the statistical error and also the systematics increasing the statistics. Yeah, I don't know if you have something to...
Well, this is basically what I tried to say on this slide, right? That to say there is a systematics wall, and these are the ways to fight the systematic wall. So either you go to measurements, as I say in the beginning, that are very rare, and I showed many examples, and then by definition you're not systematically limited. Or what I mean here by calibration, tuning, cross-checks, constraints, this is what you describe, for example, as data-driven methods. I mean, use the data, use the many data to learn more about your measurement. And that learn more about the measurement means reduce the systematics. So all this needs work. Yeah.
To me, the biggest challenge of this project is not what we know or think we know we can produce, that is the new detectors that will cope with this higher luminosity and all the related technical issues, which are challenging, of course, but they are there. We think we can address them. To me, the biggest challenge is to have a 10-year program of study where each new year will not bring what has happened in the last 7 years of the LHC was an incredible new excitement every year, because we increased the energy from 7 to 8 to 13 TeV and next to 13, and the luminosity scaled up by big leaps every new year. So every new data set brought with itself big new possibilities for discovery. If we fast forward to 2030 or so, when we'll have collected, say, 1.5 aptobands, inverse aptobands of luminosity, and the next year will produce a relative increase in the precision of maybe 2 or 3%. This is, to me, the biggest challenge, how to sociologically keep together a big experiment which will not have the same amount of enthusiasm. What do you think about this?
I agree. I mean, this challenge is huge. This challenge is huge. I completely agree. There is one aspect to it. I mean, it is true in these last years we were always in a lucky situation that every new year gave us a kind of a completely new type of data set. There is one kind of disadvantage to this, or let's say there's an advantage of going into a regime where, let's say you hit the square root of n curve. And this is something which we hear very often, especially also from the young people, that so far, in these last years, somehow we did not have any more time enough to think, really, to do, as was I said on the last slide, think really about completely new methods, new ideas, and to implement. Even somebody might have, I'm sure that there are ideas around, people don't even have time to implement them. Now, if you're in a regime where your data set is not going to be doubled or you have a new energy, this helps in this respect. At least there is then time to think. Of course, I agree with you. At some time, you run out of stamina, even with the thinking. And then we have to see. Of course, it also depends what happens with the measurement. course, if something turns up, then it will be easier. If nothing turns up, I agree, it will start to be very tough, because operating this detector is very difficult. It will get more difficult when the detectors start to degrade again, and you cannot do it with 5 people.
Okay, this is not a question for the students. Related to this issue, I think that there is a much more problematic question. That means the new project. I mean, I do not really follow the meaning of Michelangelo's slide, because if we are in 10 years from, or 15 years from the end of high luminosity, we really need to start now thinking the new project.
This is
we can, yeah. So, and this is a big problem for CERN and Europe. And,
absolutely agree, and this is happening. So actually, people have started to think of the next project. I mean, there's this whole FCC study, there's the linear collider discussion in Japan, there's discussions in China.
Europe.
I mean, but it influences a lot what people also think in Europe. And in 2 years from now, we will have European strategy discussions. And for example, one very important development will be that I think CERN for sure will have to continue investing on the development of new superconducting high field magnets to at least keep open the possibility that at least we have the technology in hand for our next machine, independent of political discussion and so on. I agree. I mean, the long-term future, it's a very difficult moment, and these discussions in the next few years will be pretty interesting.
Okay, so probably just you know, wine and cheese kind of question, but you know, the way we looked at new physics so far, we seeked for new physics so far. That is basically going to our theory colleagues, asking them
a bit louder?
Asking them a question, asking them what could be the a possible model or framework, theoretical framework for the new physics phenomena. And we got back to our experiment, and we actually checked our data, comparing the 2 hypotheses, the one provided by the theorist, the given one provided by the theorist, and the standard model. Okay, and that was, and it's still be the way we are looking for new data, right? So we were checking, every possible alternative scenario one by one. So we haven't found anything, but we saw many cases, like the most I think relevant one was 750 X's, where nobody actually pointed the finger there on the theory community. We found that actually our prior for that was very low, saying that nobody pointed that the finger there. Why should be that thing be relevant? But the excitement in the theory community was huge, right? So that actually made us changing a little bit our mind, saying that probably the way we are looking for new physics is not so inclusive. So what is your personal feeling about how much inclusive you've been so far? Looking for new data. I mean,
yeah, it's difficult.
Translated that and say,
as you know,
could it be the case that we actually missed the new physics in the data we got so far?
There's always a likelihood. I mean, there could be something that we trigger on something which is there, we just don't trigger on it. There have always been these attempts to make this very inclusive model-independent analysis, and they are there. So at least I think we can say somebody is trying it, but they also differ. I mean, we have a statistics expert here. Once you start to look at so many bins and trying to look for everything, it's easy to get excited maybe about some deviations which are there, which maybe are not so important. So I think 2 things. I think the theoretical guidance will continue to be important. I think so, because in the end you have to design your trigger in one way or the other. To completely being blind on the trigger level, at least, I cannot really imagine. Second thing, and here I'm just thinking out loud, maybe I'm saying completely stupid things. Maybe this revolution now with machine learning algorithm, maybe this gives us a new way of looking at the data in a more model independent way. Maybe, I don't know, but could be.
Yeah, indeed, there will be, one of the seminar will show also a possibility to be sort of triggerless, which is not exactly triggerless, but sort of triggerless, so reading everything that comes in and then leaving later the possibility of decide that. We cannot do that on the full data set, but it's already on a quite significant data set, so that's a very big technological challenge, but could indeed leave the opportunity to have a more wide approach and not targeted to anything, indeed. More questions?
Short question. So what about the possibility to increase the energy for the luminosity? You have some recent news? Because, I mean, your nice plot, it would be much better to have a lower coefficient.
So I don't know how much I'm allowed to say in the sense that how official things are, but I know when people at CERN are looking into some tricks how to increase the LHC energy by a bit, maybe 1 or 2 dB, by putting at least a few of new high field magnets. You don't have to replace the full machine. So with some tricks, one can increase a bit, and yeah, people are looking into it. How far they will go, and when it will happen, if ever, I don't know, but they are looking.
In any case, to increase substantially the energy, even in the LHC tunnel, you need techniques for the magnets which are not ready now, which are being developed, and more or less they are expected to be ready around 2035. So that fits also very well with the present scheme. So in any case, we could not say let's give up the high intensity focus on high energy, because we don't have really the technologies ready at the moment. We have to change the technology with which the magnets, the superconducting magnets are done, and it's happening because also for high luminosity LHC, some of this has to be introduced in the interaction region, for instance, but will not be ready in less than, let's say, 15 years or something, or 20. So there is an outlook, but it's an outlook which matters more for the student than for me. So if there is no other question, I think we should thank again Gunther. And I really hope that you have seen that there are big challenges in physics, but also in technology, detector, big investment, also from Italy. Padova is in this business quite significantly, so I hope that people will come also to follow the more technical and specialized seminar in which we will highlight a little bit more the plans. Thanks to everyone and to Gunther.